So now that we have a notation that says do the area under the curve, all right, there was a handout early in this section. It was just kind of written out in words, find the area under the curve of this function between here and here. But now we can just use the notation to say this. So the integral from 3 to 6 means find the area under the curve of this function. So right now the dx isn't really important. That's just saying what the variable we care about is. For right now, it's pretty much always going to be dx because that's the variable we use the most. But if you were to graph this on Desmos or by hand, it looks something like this. And of course, my drawing's not going to be very good, but it looks like that. All right, so this is a circle, kind of the top half of a circle. All right, we want to find just the area from 3 to 6. So 3 is here, so we want to find this area under the curve between the x-axis and our graph, all right, from 3 to 6. But we know the area of a circle is pi r squared. So if we were to kind of have this whole circle, that area would be pi. The radius, this distance here, is 3 times 3 squared, which is 9 pi. All right, so this whole circle would have area 9 pi, but you can see this is kind of just the top right of the circle. So our answer is going to be a quarter of this, 9 pi over 4. All right, so the area under the curve of this specific one, which ends up being the top half of, or a part of a circle, is 9 pi over 4. All right, here, again, for right now, we can only use kind of geometric principles to solve these problems. So if we look at what this graph is going to look like, all right, 2x plus 3, if we look at the graph, it's a line. The y-intercept is going to be 3, and the slope is going to be 2. So if I go up 2 over 1, that'll give me my next point, and that's going to give me a line like that. And I want to find the area just from 2 to 4. So I start at 2, and I go until 4, and I'm going to try to find this area here. And you have a lot of different ways you can find this area. You can kind of use bigger and smaller triangles. The way I'm going to do is break it up into a rectangle and a triangle. So I have this rectangle here, all right, in red, and then this triangle here. And now I just need to label all the sides. So the width of the rectangle and the width of the rectangle, or the width of the triangle is 2, because it's going from 2 down here to 4. The height of the rectangle is when I plug in 2 and go up and hit my function. So if I plug in 2 into this, we get 4 plus 3, and that's 7. So the height of the rectangle is 7. And the height of the triangle is from when I go from the point at 2 to the point at 4. So I plug in 4. I get 11. Well, if 7 gets me here, then to get up to 11, that needs to be 4. So I can just put this together. My rectangle part is a 2 by 7 rectangle, that's 14. My triangle part is a 2 by 4 triangle, so that's going to be 4. Because it's 8 divided by 2, and I add that to get 18. All right, so for right now, just know that this notation means find the area of that function between these two values. And for right now, you pretty much just have to graph it and use some type of geometric principles, rectangles, triangles, circles, using all that together to get your value for what your integral should be.